Let me start. Yes, Tejas Sonavne. Any problem? You raise the hand. Can you see my screen?
Yes,
Yes,
ma'am.
ma'am.
Okay. So we have started unit number 1 in the last lecture. We have seen the syllabus of unit number 1, the different course objective and course outcome. These we have discussed. Then we have discussed the basic electronics as a prerequisite required for this subject. We have seen what are the different active and passive components, and we have discussed the example of active components as junction field effect transistors, MOSFET, BJT, light emitting diodes, the different optoelectronic devices, and so on. And we have seen the passive components like resistor, capacitors, and inductors, where we have to supply external power supply, and the power gets dissipated in this component. So these are the more power consuming um, components. Then we have seen the classification of transistors as bipolar junction transistor, field effect transistor, and insulated gate bipolar transistor. We are about to focus on FET family because we have to learn MOSFET in this second year. So you have already done with bipolar junction transistor and JFET in your first year. So now we'll be dealing with MOSFET. There are two types of MOSFET we have seen, that depletion enhancement MOSFET and enhancement only MOSFET. D and E MOSFET. Okay. So we have seen the difference, difference between these MOSFETs. We have focused on differences between the bipolar junction transistor and field effect transistor. So there we have observed that bipolar junction transistor, it consists of or there are two types of charge carriers which takes part in current conduction. So that is why it is called as bipolar junction transistor. Whereas in the FET family, there is only one types of carrier that are contributing to the current. So because of this, what happens if you see the speed of operation, the noise level, so you will say because of the two different types of charge carrier present in BJT, noise level is high in BJT. Noise level is high in BJT as compared to the FET family. The speed of operation becomes slower because of presence of two carriers. Because if you are using BJT as a switching element, then you are driving it from cutoff to saturation, saturation to cutoff to make the switch on to off and off to on. So in this case, the charge carriers, they are combining with each other. Then again, they are separating when you are switching the device from one to another state. And therefore, it takes a time. Therefore, speed of operation becomes slow in case of BJTs and it is faster in case of FET. If you see the frequency response means how many frequencies can be amplified by a particular amplifier. In what is the range of frequency that can be amplified? So you will find the frequency response is broader. More range of frequency can be amplified by JFET or FET family as compared to the BJTs. Also, we have discussed in basic concept that BJT is a current controlled device because it is the base current who is controlling the output collector current, the output voltages and output powers. So that is why we call BJT as a current controlled device. In FET or in MOSFET. So in the FET family, it is the input voltage. Remember the basic and important difference, that FET family is a voltage controlled device, JFET or MOSFET, because it is the input voltage which is controlling all the output parameters like output current, output voltage and output power. So that is why we call it as current controlled device, sorry, voltage controlled device. Got it? So these basic differences we have seen. Yeah, thermal runaway. We have discussed thermal runaway also, that it takes place in BJT and because of absence of minority carriers, FATE does not suffer from the thermal runaway problems. Okay. Yeah, so we have started with the discussion of construction of MOSFET. Okay. So MOSFET construction, we have seen, we are learning N-channel enhancement MOSFET. Okay, N-channel enhancement only MOSFET. So if you see the construction of this MOSFET, that there is a substrate. Initially, there is a substrate or the body which is doped with P-type semiconductor. Okay. In this substrate, we form two N-type blocks. Okay, and the doping concentration of these N region is higher as compared to substrate. So substrate is comparatively lightly doped, and these two regions which are formed inside the substrate, these two blocks are highly doped with N-type semiconductor material. Plus sign, excuse me, plus sign indicate here high doping, right? Now this is coated with this substrate is then the substrate is coated with SiO2 layer, and then what to do? We take out some part of this SiO2 layer and dope the metal to take a contact or to form a terminal from these two N blocks. We call these two blocks as source and substrate respectively. Now there is a region where there is nothing in between these two. Remember, I told you, I have explained you that the current will flow from source to drain internally. Source means provider. Drain is a collector. Source is a provider, so it will provide the electrons and that will go to drain. But now how they will go? Because in between there is no N-type of N-type channel present. N-type channel is absent here. So how they will go? So there must be some something that will develop the path. Okay. So now what is done? There is an empty space between two N blocks. Above that space, on the SiO2 layer, metal is deposited and we call that metal as gate. Then we take combinedly the terminals, one from source, one from drain, and this is the gate terminal. Moreover, we also take a contact or a terminal for P-type substrate. So 1, 2, 3, 4 terminals are there, and the names of these are source, drain, gate, and substrate. In general, we used to connect source with the substrate. Okay, this much part we have discussed. Is it clear? Is it clear? I have revised all
Yes,
whatever okay. Now we will see how to bias this. Now you know that when this MOSFET is formed, so there is the junction. This is N region and this is P region. So in between N and P region, there develops a depletion layer. So here also there is a depletion layer and here also there is a depletion layer. Remember that I have not connected any power supply till now. So this is the basic construction. In short, you can explain it as N-channel enhancement MOSFET is formed in a P-type substrate. In this substrate, there are two N blocks doped. The doping concentration is higher here, and these two N, that metallic contacts are taken out from these two N blocks, and we call it as source and drain. In between the source and drain, there is no physical channel present. Above this region between source and above the region between and drain, we deposit metal just above SiO2 layer, and this terminal is this metallic contact is called as gate terminal. There are source, gate, drain, and substrate terminal. In general, source is connected with the substrate, and there are depletion layer established between two PN junctions. Okay. Now let's move further. We will see how to bias this. Okay, how to bias MOSFET. Okay. Now, as I told you, source is a provider and drain is a collector. So current, internal current is about to flow from source to drain. See, the external current is a conventional current. which flows from higher potential to lower potential. The internal current in this case, it is constituted of electrons. It will go from source to drain. Just a minute, please. It shall go from source to drain. Now, source shall provide and drain shall receive. So how shall I bias the source and how shall I bias the drain? Because drain has to collect, it must be connected with the positive potential. Because drain has to collect, it must be positive. Because what are here? Electrons. So this drain terminal must attract the electron. That is why drain is made positive with respect to source. So what this source will do, it will provide the electron. Electrons will be pushed from here and drain will attract this electrons. Once the flow of current is established, right now current there is no current established. So remember that you have to make drain positive with respect to source. Can anybody tell me that if it is a P channel MOSFET, so what shall be the polarity of the drain? If this would have been a P-type P channel MOSFET. When I say N channel MOSFET, remember source and drain, they are of N type and channel established will be of electrons. When I say P type, then source and drain will be of P types and channel established will be of hole. So when this is a positive, this is a P type region, then there are holes, and to attract the holes, your drain must be negative. Got it? Is it clear? What shall be the polarity of drain terminal? Is it clear to you?
Yes, ma'am.
Yeah. So when it's a N channel MOSFET, your drain is made of N type material. It is providing electrons. So your drain must be positive so that it will be able to attract that electron. Okay. So now you understood that in order to establish the current drain must be kept positive. What about gate terminal? Now we will see how this gate is playing a role. So what we will do, first of all, we will connect we will short the gate with source. The voltage which I am applying here, I will call it as VDD, that is supply voltage, or the volt as I am connecting it between drain and source, I will call it as VDS. Okay, I'll call it as VDS. So what I will do, I have to observe how the current is flowing in the MOSFET. What is this relationship? So what I will do, I will connect gate with source. I will simply short it. I will keep VGS equal to 0 and I will apply VDS. Okay. So now with reference to this, we will discuss now further. So I have tried to show you here the three-dimensional diagram, how MOSFET looks like. So, you know, this is, look at the cursor, this is N region, this is another N region. In between these two, there is an empty space where our channel is about to establish. Now, the metallic contact which is taken the metallic contact. So see, if you cut this MOSFET and if you see, so you will find the metal deposited over this N region. So inside there is a N region. This is the width and this is the length of this MOSFET. Okay, so wherever there is N region, above that N region, there is metal deposited and it becomes a source. Similarly here, about the drain, metal deposited to form a contact and it is your drain. And In between this, above this space, there is SiO2 layer, and on the SiO2 layer, above the SiO2 layer, there is metal deposited, which is called as gate. So I have shown you. So now I will try to show you. So we will observe this effect. What we have done first, I have made VGS, means gate and source. The voltage between gate and source is equal to 0 volt. Okay. When I made this, now let us see what is the effect on the MOSFET. Then I have made drain positive. So I have applied proper VDS. Let us say I have applied 1 volt here. Then I will further apply 2 volt. Then I will further apply 3 volt. I will see what happens. Now I am making drain positive. I have made drain positive, so it should able to attract the electron. Fine. I have made source negative, so it has tried to push in these electrons. But there is a depletion layer in between here. Okay. So, and there is the p region presented. So how this electron will move further? Not possible. So when you are making your gate voltage 0, no current is established here, because there is no way that the electrons from source will reach to the drain. There is no way. So even you apply 1 volt, more 2 volt, 3 volt, there will be no current conduction flowing. There will be no flow of current will be established. Fine. Now, what we will do next? We will make gate terminal positive. Okay. Now, what I have done, I have applied I'll make gate terminal positive. So this is plus, this is minus. Please forget about this. White color. Now it looks like separation. So I am making gate positive. Now, when I make gate positive, what happens? I made gate positive. Second case, what I made? VGS equal to, let's say, plus some positive voltage, let's say 0.5 volt or something, a small voltage I have given. So when I give small positive voltage, what happens? You know, this is a substrate. In this substrate, there are electrons, okay, as minority carriers. Electrons are present in minor number, okay, and I am applying positive charge on the gate. So what will happen? This gate uh, will produce some attractive force. There is SiO2 layer. This is SiO2, insulating material. But this is exerting an attractive force. So what this electron will do, it will try to move towards the gate. Okay. It will try to move towards the gate. Okay. But still there is no channel established. And therefore, if the gate voltage is very small, if the gate voltage is very small, again there will be no current conduction. What I have done, I have applied proper value of VDS. Let's say I have applied VDS equal to 1 volt, and I have applied VGS, which I will say it is less than the voltage called as VT. Now what is VT? I will explain you. but you understand that it's a small voltage, and currently VGS value is less than some voltage called as threshold voltage. And therefore, even though your gate is exerting attractive force and these electrons are started moving towards gate, still there is no channel established. Further now, what I will do, I will increase the gate voltage. Let increase the gate voltage equal to VT. Let's say VT value is defined for the MOSFET. Okay. Let's say value of VT is equal to 1 volt. Okay. Now I have made the gate voltage equal to, let's say, 1 volt. Now what happens? The electrons which are present in minor number, they start moving towards the gate. But they, sorry, this is not. This is your SiO2. So these electrons starts moving towards the gate, right? It comes here. But what happens, because there is SiO2 material here, so it cannot go to the gate terminal. So what will happen? They will simply gather here, just below SiO2 layer. They will start gathering. Okay. Now, when this gate voltage was equal to VT, or I will say when I apply sufficient positive gate voltage, what happens? The electrons, they are gathered just below SiO2 layer. Now these electrons, they are present in between source and drain. Already there are negative electrons present in the source. Okay, and now a virtual channel is established. See, we have not doped their N-type material, but now our electron has deposited here just below SiO2 layer, and they are connecting this region with this region. So a virtual means some imaginary channel has been established here. Now, when it was established, when, or I will now define a parameter called as VT, threshold voltage. So this threshold voltage is defined as the minimum gate to source voltage. Gate to source voltage means VGS. So minimum value of VGS that is able to form the layer of electrons, to which we call this layer as inversion layer. We call this as inversion layer. Are you getting? Yes or no? Everybody? Everybody, please
Yes,
let me know. Are you getting?
yes, ma'am.
Okay. So the layer of electrons which is established just below SiO2 layer, that is called as inversion layer. Okay. And I will now define VT. What is inversion voltage? Layer of electrons that is established just below SiO2 layer in N-type MOSFET, N-channel MOSFET, that is called as inversion layer. And the minimum gate to source voltage that is required to form this inversion layer is called as threshold voltage, VT. So what is threshold voltage? This is an important definition. The gate to source voltage, the minimum value of gate to source voltage required to establish inversion layer, that is called as gate to source voltage. So when you apply VGS at least equal to VT, such type of layer is established. And now when you are provided VDS, suppose you made now VDS equal to 1 volt, now what will happen? The current will start flow, because this source is negative, it is pushing, this drain is positive, it is attracting, so these electrons will flow. When this layer is established, the resistance of this path has lowered, and these electrons are now able to flow from source to drain, and then the current is established. So from source to drain, current conduction will start. But if your VGS is less than VT, then whatever VDS you are applying, there will be no current conduction takes place. Okay. So I will try to plot the VI characteristics. Let I plot here itself. Now we will plot VI characteristics of MOSFET. VI characteristics means relation between voltage and current. Okay. Now I can call the characteristics, I can label the characteristics as output characteristics or input characteristics or transfer characteristics. Okay. Now output characteristics means I'll be taking output current and output voltage. Means I have to see the relation between output current and output voltage. Then I will call that characteristics as output characteristic. This is applicable to all the electronics devices where you are about to plot VI characteristics. When I want to see the relation between input voltage and input current, I will call them as input characteristics. And now, if I want to observe the relation between input parameter and output parameter, I will call it as transfer characteristics. Understand? 3 terms I told you. Are you there, everybody? Please tell me.
Yes, ma'am.
Okay.
Yes,
Yes,
ma'am.
ma'am.
Okay, good. Can you see your attendance? Is the attendance mark?
Yes, ma'am.
Okay, good. So I told you 3 different types of characteristics one can draw. So here onward, remember throughout your degree that input, output, and transfer characteristics refers to what relation. Now, if I here I'm interested to find output characteristics first. So it will give me the relation between output current, that is drain current, and output voltage. So now remember, drain, you have to make drain as an output terminal. So generally common source configuration is preferred, like you are using common emitter. So this is like the emitter of a transistor, source. This is like collector of a transistor, drain. And gate is a controller. So it is like base of your transistor. Who has the control? Now we will see, you will come to know. Okay. Now I want to see the relation between ID and VDS. ID versus VDS. Can you see properly whatever I am drawing?
Yes, ma'am.
Yes, ma'am.
Yeah. Now what I will do, first of all, now see, I want to observe relation between ID and VDS. But there is one more thing, ID changes. When you make this VDS more positive, of course your drain current will be higher. But who is controller? Gate is controller. Therefore, ID is dependent on gate voltage as well as on the drain current. So, sorry, VDS, drain to source voltage. So what I have to do, I have to keep one thing common, one thing constant, and then I will observe the relation between two. So let us make your VGS. Let's say the value of VGS, first of all, is less than 50. So what happens here? There is zero gate current. Okay. On this axis, current is zero. What I made? VGS is less than VT. So I'm not getting any drain current. I made VGS less than VT and I keep on increasing value of VDS. Let's say 1 volt, 2 volt, 3 volt, 4 volt, and so on. Let's say 15 volt. But will the current flow? No, because VGS is less than VT. Therefore, there is no voltage is, sorry, no inversion layer is established. There is no channel is formed. Therefore, there will be no current. Therefore, this region where there is no current flowing, or the region below VGS less than VT, we call it as cutoff region. Cutoff region. Okay, got it? Now I will make VGS greater than VT. So let's make it VGS equal to, let's say, 1 volt. So when you make VGS equal to 1 volt, you will find that as you are increasing VDS, your drain current is initially increasing linearly. First of all, the current is increasing linearly and then it becomes constant. Then it becomes constant. Now, why this is happening? So you have studied pinch off term in case of FET in first year. So here also same thing happened. So when you are increasing VDS, first of all, the current start flowing like this. So channel is established, no problem. Channel is established now. So current has started flowing from source to drain, and the path is completed. Okay, and you have applied here some VGS. Okay, so please ignore this line. I have included for animation. So now we are applying VGS. This short line indicate VGS equal to 0. Okay. So now what happens when you are increasing VDS, drain to source voltage? Okay. So this is your drain terminal, and here you are applying positive, right? And source and gate, they are common, and we will ground it here. Okay. I have grounded source. So I will say drain is positive with respect to source and gate is also positive with respect to source. Now tell me, these are the two regions. This is your source and this is your drain. So when I am increasing VDS, this voltage, positive voltage is increasing. So which of these block? I have applied here positive voltage, and substrate is at, see, substrate and source, they are combined. Okay, source is at ground, right? Can you see? A source and ha substrate. Substrate and source, they are grounded here. So this P substrate, it has ground potential, and this N region is positive. Okay, whereas the positive voltage is that is experienced by this region is very less because I have grounded. This is negative and it is grounded here. So now you know the concept of reverse bias. When a PN junction is reverse bias, this is P region, this is N region. So when you connect P to negative terminal, P to N and N to P, right? Then you say it is reverse bias. So now you have connected N to P. This N region is positive and substrate is, it is with respect to substrate, this drain is more positive. As when you are increasing drain, it becomes more and more positive. That means the reverse bias here increases highly. The reverse bias at this junction is increased. Therefore, depletion layer here it will be more. The depletion layer which is establishing at here will be more as compared to the depletion layer which is establishing here. Therefore, what is happening? इथे डिप्लेशन लेयर कमी आहे आणि इथे डिप्लेशन लेयर जास्त आहे. तर तुमचा चॅनल कसा होतं बघा. The channel width will be larger here and it is smaller here. The channel, I will draw, this is the depletion layer now here, and the depletion layer present here is smaller. Okay. So if you see channel, this is depletion layer. It means available channel is less here and available channel is more here. So if I want to draw the channel, this will be like this. The channel baga. The channel is broader near the source and it is very narrow near the drain. Lakshat ala? Understood? Because drain is facing more reverse bias, therefore width of depletion layer is more here. When you say depletion layer is more, it means the available width for channel is less. So here the channel is narrower and here the channel is broader. So this how now they are not symmetrical. Atta symmetrical nahi hai. When they established the layers were depletion layer were symmetrical, but now it is not. Now, when you go on increasing, what happens actually? So this becomes still more wider and wider, and there is only one point that is touched here. So simply these electrons are pushed to drain through this limited region, and we call this as channel is pinched off. Channel is pinched off, and therefore the current now becomes constant. So when there was a wider channel, the current was increasing. When there was a wider channel, the current was increasing, and when there is and show here. So when the channel was wider, the current was increasing linearly. Look at this portion, linear increase. And after it is pinched off, the current remains almost constant. Okay. So we get these characteristics when you keep VGS equal to 1 volt. Here I am taking some random value so that you will understand. Okay. Now, again, I will repeat the experiment and I will make VGS equal to 2 volt. Okay, what I will do, I will increase value of VGS. Now, when I increase value of VGS, what will be the effect on the channel? Can anybody tell me? The first case, there was some channel established when VGS was 1 volt. Now, I am applying VGS with 2 volt. I am increasing positive voltage. Can you tell me what will happen to the drain current or what will happen to the width of the channel? In this case, will it be more or less as compared to the first case? Please, everybody unmute yourself and try to answer. Don't hesitate to give the answer. Are you there?
It will decrease.
Speak loudly, please. I am not able to hear.
It will decrease.
What will decrease? Current or channel width?
Channel width.
Channel width. Okay. Anyone else? Anyone else would like to answer? Yes. Aditya Pawar, अक्षय सुतार, हाथ का दोगे?
Yes, ma'am.
What will happen?
Ma'am.
What will happen to the width of the channel? First case, I applied here gate as 1 volt. Okay. Now, so when I applied 1 volt, say this was the width of channel. Now I am making it 2 volt. So what will be the effect on width of channel? Someone has said that it will decrease. You have applied more potential, more positive potential. Yes, Arpita?
Ma'am, current increases.
Current increases? You say whatever you wish, don't worry. But please answer. Chetan Patel? Chetan Patel is absent. Prathamesh Patel? Prathamesh Patel? Absent.
Yes, ma'am.
Okay, what is your opinion? When I have increased gate voltage, what will happen to the width of channel which is getting established here? Are you listening, everybody? Rishikesh? Now tell me, when gate... Yes, somebody is trying to answer. Yes, Rishikesh? When gate is more positive, will it attract lesser electrons or more electrons? जेवढा गेटला तुम्ही पॉझिटिव्ह करणार आहात तर तो जो अट्रॅक्ट करणार इलेक्ट्रॉनला तो जास्त करणार की कमी करणार?
जास्ती करेल.
Right, it will more you make gate positive, it will offer more attractive force. In first case you made it 1 volt, now you made it 2 volts, so it will attract more number of electrons. So more number of electrons will gather here, therefore channel width will increase, and when the channel width is increasing, then the current will also increase. If you make gate 3 volt, so in that case again your channel width will increase and therefore more gate current will flow. So when you keep on increasing gate voltage, it is attracting more and more electrons. So in every case, you will get more channel width, and if the space available for conduction is more, so more current will flow. See, if the space which is available, previously this was the channel width. So this was the space, this was the space available. Okay, so current was flowing through this space. Now in second case, when you make it higher than 1 volt, so this is the width of channel, it becomes, so more current will flow. If you still make that gate to source voltage, now see this much width is available. Okay, previously this much width was available, then in second case it was increased, in third case it is again increased. So similarly, eventually your ID will also increase. So more you make your gate positive, more electrons will be attracted, larger will be the width of channel, and therefore larger will be the drain current flowing. So when you draw the output characteristics, you see when your VGS is 1 volt, you get here the curve over here. When you increase VGS, the behavior is same. Initially, the drain current increases, then pinch off happens and the drain current becomes constant. But you find that the curve which you plot for 2 volt, it is above 1 volt. The curve which you plot for VGS equal to 3 volt, it is still above this curve. So higher is the voltage, the topper will be the position of the curve. Right? Now see, cutoff region, you understand that when value of VGS is less than VT, so there is no current conduction. So in this region, there is no current conduction, and this region is called as cutoff region. Now you see when the drain current is constant, the region of these characteristics, when the drain current is constant, is called as saturation region. Understand? And the region where the drain current is increasing linearly, linear increase means following Ohm's law. V is directly proportional to I. Okay, so that is why we call it as ohmic region. So the region where the drain current is increasing linearly, it is called as ohmic region. So you have to show 3 region: ohmic region, saturation region, cutoff region. Okay, now I will ask you some questions. Now you have to answer me. Everybody has to unmute and try to answer. Do not leave the meeting as I am asking you questions. Okay. What are the 3 different names that you can write on the drain characteristic? The output characteristic can also be called as drain characteristics. Okay, so these are, I will either call as output characteristics or drain characteristics. Tell me, what are the names of different regions on the characteristics of MOSFET? It is there in front of you. Come on, quick. Unmute yourself and answer the question. Hello. Name the different regions on the VI characteristics of MOSFET. Characteristics is there in front of you. Unmute everybody, please. Yes, Prathamesh.
Ma'am, cutoff region, saturation region,
And ohmic region. This is ohmic. Very good, Prathamesh. Cutoff, this is cutoff, this is saturation, and this is ohmic. Next question. Which region is called as ohmic region on the VI characteristics of MOSFET? Anyone else? कुठल्या regionला ohmic region म्हणायचं? Please don't waste time. Quick. So let me introduce you. Yesterday there was induction program, but as I was having the lecture, I could not attend it. So I will brief you about some club. But let's finish it. Then I'll be telling you. Which region is called as ohmic region? Yes, Mia Lal. Absent. Kalpesh.
Yes, ma'am.
Which region can be called as is called as ohmic region? Define. काय असतं त्या रिजन मध्ये? कशावरून कुठल्या रिजनला तुम्ही ओहमिक म्हणणार?
सॅच्युरेशन रिजनला.
सॅच्युरेशन रिजनला ओहमिक म्हणणार. सॅच्युरेशन रिजन इज डिफरंट, ओहमिक रिजन इज डिफरंट. साक्षी, समृद्धी, पेजल,
The region which has linear increase in current, means which
very
follows
good.
Ohm's law.
Correct. The region where drain current increases with drain to source voltage is the ohmic region. How you will define saturation region? पार्थ सावंत, तुम्हाला काय दिसतंय इथे? Yes, या
ma'am.
फिगर वरून. Yes, Parth. To which region you will define as saturation? Define saturation region on the characteristics. What do you observe in saturation region? Yes, Parth. How the drain and drain current is behaving with VDS, drain to source voltage. Pejal said that drain current is increasing linearly with respect to VDS, so that is a ohmic region. Now tell me about saturation region. Saturation region. Anyone else? Sanjay? Sanjay?
Yes, ma'am.
Define saturation region. तुम्हाला काय दिसतंय त्या region मध्ये? How is the relation between ID and VDS?
मॅम ते क्लोज स्विच सारखं.
क्लोज स्विच सारखं आहे, मीन्स कॉन्स्टंट करंट आहे. क्लोज स्विच असणे म्हणजे काय? कॉन्स्टंट करंट असणे. You related it with your transistor terminologies, right? You are correct, but you should define that the region where drain current is almost constant with VDS. So even though you go on increasing VDS, after pinch off happen, the current remains constant. Okay, and who will define
Yes.
cutoff? Anyone? Cutoff region? So Yash, please answer at your own. Cutoff region.
Ma'am, when the input is 0.
Not input is 0. I have applied VGS. It is very small. I have applied DC voltage as VGS, but it is very small, less than threshold. I may apply input voltage, some positive input voltage, but it will not amplify it, right? It is the region where drain current is 0, simply. Okay, drain current is 0, or MOSFET is not conducting, or the region where VGS is less than VT. VGS is less than threshold voltage is called as cutoff region. So you understood this VI characteristics or drain characteristics of MOSFET. We call it as output characteristics. Now I told you the transfer characteristics. When I have to observe the relation between the voltage in output current and input voltage, because you see the current changes with VDS. Here it increases linearly, then almost become constant. So till here it depends on VDS, and it depends on VGS also. When VGS is more, you get more current. So you have observed the relation between ID and VDS by keeping VGS constant. Now I will observe the effect on output current. Output current when we vary input voltage. So output current versus input voltage. This characteristic is called as transfer characteristic. Okay, this is called as transfer characteristics. Now you have observed that when you apply VGS, but VGS is greater than 0 but less than threshold voltage. Look at the portion here. So there is no current flowing. ID is 0. ID y-axis वर आहे. So इथे ID ची value काय आहे? 0. ID is 0. So when VGS is less than threshold voltage, VGS T, or VT, there is no current. But when you start increasing current, the current increases linearly with VGS. VGS वाढवला, current वाढला. When you again increase VGS, current increases. When more value of VGS, more is current. So this is the transfer characteristic. Okay. So we'll stop here. Have you understood? Unmute yourself and tell me. Now you have to study the things at your own. You have to revising. I am having a good video, but I don't think that you are not able to see the audio, right? You are not able to hear the audio for this video. Okay, I'll try to show this on some different PC. I'll share as a revision. I will show you, and I'll send you the link of this video also. So here animation is shown, and if you see, you will definitely enjoy this, and you will remember the things. Okay, I'll try to share the link with you. Okay, so let's have attendance now.